When you learn ordinary quantum mechanics, you start with systems that are simple and isolated. If you need to describe a single electron orbiting a single hydrogen atom, standard wavefunctions work perfectly. You map its position, calculate its momentum, and track its probability distribution over time. But the material world is not made of isolated atoms. If you want to model a small block of metal, a highly practical engineering task, you aren't dealing with one electron. You are dealing with 10 to the 23rd power of interacting electrons, all moving at once. Applying our standard wavefunction approach to this crowd reveals a severe physical problem. Identical quantum particles have no identifying features. Unlike billiard balls, you cannot paint a red dot on one electron to track it. An electron is an electron. Labeling them electron 1 and electron 2 is an artificial human construct with no physical reality. Look at the math for two identical electrons. To enforce indistinguishability, we manually write out their coordinates and hard code a minus sign between them. Scaling to n particles requires calculating every possible permutation, triggering a massive factorial explosion of mathematical terms. The sheer volume of data becomes impossible to compute. Ordinary wavefunctions break down completely as a practical tool when forced to track the individual trajectories of massive numbers of identical particles. To model complex matter, we have to abandon the idea of tracking individual particles entirely. We have to stop asking which electron is in which state. This chart visualizes why the old way is so chaotic. Trying to map specific numbered particles to specific energetic states creates a tangled web of overlapping probabilities. It assumes individuality where none exists. So we change the question. Instead of asking where particle number 3 went, we ask, which quantum states are currently occupied? Look at the right side. The focus shifts to the states themselves, acting as distinct slots. Particles are anonymous units that fill or leave slots empty. We describe the system by listing slot statuses: occupied, empty, occupied. This approach is called the occupation number representation. In physics, it's also known as the Fock space formalism. Second quantization is a mathematical basis shift, moving our analytical focus away from the trajectories of specific objects and toward tracking the active status of an environment. Moving into this occupation-based space means we need new mathematical tools to manipulate it. We need a way to change the status of our slots. We start with a mathematical baseline called the vacuum state. It is written as a 0 inside a ket bracket, and it represents a completely empty environment, with no particles present at all. To populate this environment, we introduce our first mathematical tool, the creation operator, denoted by a variable with a dagger symbol. As shown in the top row here, when the creation operator acts on the vacuum, it spontaneously generates one particle in a specific state, changing our empty tray into an occupied one. Its exact mathematical inverse is the annihilation operator, written without the dagger. Down here in the bottom row, the annihilation operator acts on a state that already contains a particle, removes it, and returns that specific slot to empty. Notice how active this is. Standard momentum or position operators in early quantum mechanics are essentially measurement tools used to extract probabilities from a wavefunction. Creation and annihilation operators are completely different. They represent literal, physical transitions of the system from one reality to another. By combining these two operators, you form a complete mathematical engine. You can describe any complex sequence of quantum events by simply chaining together the creation and destruction of particles. This engine solves the scaling problem by hardwiring the laws of physics directly into the algebra. Take electrons, which belong to a class of particles called fermions. The Pauli exclusion principle strictly dictates that no two identical fermions can ever occupy the exact same state at the same time. As we clearly saw earlier, enforcing that rule the old way meant manually tracking negative signs across massive equations. Second quantization handles this by applying a specific algebraic rule to fermion operators, anti-commutation relations. If you attempt an illegal move in this framework, say applying a creation operator to a slot that already contains an electron, the math physically stops you.
Because fermion operators anti-commute, any creation operator squared automatically evaluates to exactly 0. The math doesn't yield a tiny probability for an illegal state, nor does it require you to manually insert a rule to prevent it. The state simply ceases to exist in the underlying equations. Second quantization completely automates the heavy lifting. The Pauli exclusion principle ceases to be a manual chore we impose on the particles, and instead becomes a structural, inescapable feature of the math itself. This structural approach also provides a unified language for all particles. Consider bosons, like the photons of light or the phonons carrying heat through a crystal. Unlike fermions, bosons have no capacity limit. They actually prefer to pile into the same state infinitely. This graphic illustrates the contrast. The fermion tray strictly holds a 0 or a 1. The boson tray is an infinite stack. To model light instead of matter, we keep the exact same mathematical occupation framework and simply swap the algebra. By changing anti-commutators to standard commutators, the previous capacity limits vanish, and the math flawlessly adapts to describe bosons. But the most important advantage of this language is counting. First quantization assumes that the total number of particles in a system never changes. In dynamic reality, particle counts are constantly shifting. If you heat up an atomic structure, it emits a photon. The total number of particles in the observable universe just went up by 1. Standard wavefunctions cannot handle this. Look at this emission mapped to operators. An excited electron is annihilated and recreated in a lower state, while a photon creation operator births light. This logic holds everywhere, from electron-hole annihilation in LEDs to electrons creating phonon vibrations in a crystal lattice. Any real-world process where particle numbers fluctuate through interactions requires second quantization to be mathematically modeled. To see the full power of this language, we look at a many-particle Hamiltonian. This equation describes the total energy and behavior of a complex interacting system. In first quantization, this interaction term involves impenetrable integrals across all coordinates. Here, it is expressed as a clear string of 4 operators. We read it from right to left, like a physical story. On the right, 2 annihilation operators eliminate 2 particles from their current momentum states, labeled K and L. Immediately on the left, 2 creation operators birth those 2 particles back into existence in brand new states, labeled I and J. Taken together, this string perfectly describes a scattering event. 2 particles approach each other, interact, and bounce off into new trajectories. Complex mathematical integrals have been replaced by modular, logical building blocks. If you want to add a magnetic field, you snap on a term that creates spins pointing up and annihilates spins pointing down. Physicists use this framework because it allows them to read the behavioral dynamics of a new material straight off the page. This operator math also translates directly into the visual shorthand of modern physics, Feynman diagrams. As you can see here, there is a strict one-to-one mapping. Every incoming or outgoing line corresponds to a particle state, and every intersection, every vertex where things interact, is governed precisely by a string of creation and annihilation operators. Zooming out from individual diagrams connects this operator language to the large-scale architecture of the universe. It suggests that individual particles are not the fundamental building blocks of nature. Modern physics is built on quantum field theory. It posits that the universe is actually composed of continuous underlying fields, an electromagnetic field, an electron field, a quark field, stretching across all of space. Within this view, a creation operator describes the mathematical action of adding energy to a specific field, generating a localized ripple. We perceive that ripple, that excitation, as a discrete particle. That is the ultimate value of second quantization. It moves our mathematics away from tracking individual specks of matter and aligns it with how the universe actually operates. By describing reality through occupied states and the continuous creation and destruction of energy, it provides the precise engineering foundation for everything from the semiconductor in your phone to the fabric of